So we are now doing Chapter 17, Electrochemistry. This is very exciting. We're almost at the end. So, what are these things? They're batteries. Have you ever heard of the copper top commercial? Doo doo doo. It's a copper top. Bonk. Maybe you've never heard that commercial. Maybe that's from when I was a lot younger. But they often call batteries copper tops. You're going to find out why now. So, batteries, they're just galvanic cells. We're going to learn all about galvanic cells today. They operate by using the difference in electrical potentials in reduction-oxidation reactions for different substances. So, 17.1, galvanic cells. We're doing redox chemistry again, reduction oxidation. So, redox reactions, they're spontaneous. They could provide work, but when they happen in a beaker, just one single beaker, everything gets all the useful energy that we could have used. So it's not useful, actually, because it all gets converted to heat. So all the useful energy is not useful. It's all heat. If we take the solution where the redox is happening, and we divide it into literally two separate half cells, we physically separate the reduction and oxidation reactions, and we join them by a wire. Electrons flow through the wire, and that chemical energy is converted into electrical energy that we use to power our electronics. So you need to learn a lot of vocabulary and, oh my gosh, all these things. So over here is a picture of a galvanic cell. In one side you have oxidation occurring because you have reducing agents and they get oxidized. On the other side, you have reduction occurring, where you have the oxidizing agent. And there are two ways to set up these galvanic cells. One, you have a porous disc in between the two different containers. Another way is you have to make sure you have a salt bridge between the two containers. Something has to connect the two containers so that the solutions, the ions in the solutions, can move from one side to the other. Okay, so some vocabulary. Galvanic cells, I already talked about. The anode, that's just defined as the place where oxidation occurs. The cathode is where reduction occurs. You'll find out a little later why I've got these bold in red. A half cell is just one side of a galvanic cell. The salt bridge, this is really important. You have to know what the purpose of a salt bridge is. It keeps electrical neutrality. That's not listed on here. You should make a little note. It keeps everything electrically neutral by allowing positive and negative ions to go from one side to the other. And again, in place of a salt bridge, you could have a porous disc. Now, these pictures don't show what's called a voltmeter. A voltmeter is something that measures the voltage of the galvanic cell. And here are some conversion factors. A volt is a joule per coulomb. 96,500 coulombs is the charge of 1 mole of electrons. So a coulomb is a charge unit, and 1 mole of electrons has the charge of 96,500 coulombs. That will be important later on. There's something called a Faraday, which is a mole of electrons. So a Faraday is 96,500 coulombs. That'll come up later. So why did I have that stuff highlighted up there? And why do I have these pictures here? An ox and a red cat. Oh goodness, I'm not even recording. Yes, I am. Apparently I was recording. How embarrassing. That was my cell phone. That's the ring that... Anyway, we don't need to discuss that. It's my daughter's ring. It's a little duck. Okay, back to the video. So why did I have an ox bolded and cat red highlighted, not highlighted, but bolded and red? Because you're going to remember an ox and a red cat. An ox and a red cat. Oxidation, ox, occurs at the anode, an. Reduction occurs at the cathode, red cat, red cat. An ox and a red cat. Okay, moving on. Section 17.2, standard reduction potentials. Back to the batteries. How do these things work? They're galvanic cells where you have a half cell They're actually separated, physically separated. Down the middle you have, I can't remember if it's the cathode or the anode, and then on the outside you have the anode. And they get connected by a wire. When you connect the battery to something, you could take a wire and put it from the positive end over to the negative end, and then you would complete the circuit and the galvanic cell would start operating. Okay, I want to show you something real quick. On the AP exam you will have this chart. This is a great big chart. It's lots of information here. I just want to show you real quickly. This chart right here, you get this on the AP exam. They are standard reduction potentials. You're given all the half reactions. These are all reduction. Gaining electrons is reduction. So these chemicals are gaining gaining electrons to get reduced. F0, F -1. And then these are your standard reduction potentials for the half reactions. And you will get this sheet in class, and you will get it for the AP Chemistry exam free response section. Okay, so I've included a different set. It doesn't look exactly like the AP exam, but this is just for our notes for today. So these are our standard reduction potentials. Units are volts, which is a joule per coulomb. A joule is an energy unit. A coulomb is a charge unit. So these are our reduction potentials. And then there's this symbol. You'll see it italicized like this in your book. In the AP exam, they just write it like this, so I've got it in both ways throughout this set of notes. Then the little knot there stands for standard. It's a cell potential or energy. Actually, it's an energy per charge. So the units are volts, which is joules. Joules are energy. Joules per coulomb is energy per charge. All right. For a galvanic cell to be spontaneous, and all galvanic cells are spontaneous if the wire is connected, the standard cell potential is greater than 0, positive. So for spontaneous reactions, delta G is less than 0. K is greater than 1. K, the equilibrium constant, is greater than 1 because products are favored. And the standard cell potential is greater than 0. Okay, so E cell is equal to E oxidation plus E reduction for your half reactions. Notice these are reduction potentials. So if we have oxidation occurring, you have to reverse the sign, change the sign, which is why we add the oxidation and the reduction. So we change the sign for the oxidation reaction, and then we add that to the reduction reaction for the galvanic cell. Now, cathode, cat is red, where reduction occurs. And notice this stays the same sign, so reduction, cathode, positive. And we subtract the standard potential. The standard potential is the number you see here. We would subtract the standard potential at the anode. Anode is where oxidation occurs, so that's why we subtract the anode standard reduction potential, because at the anode we have oxidation occurring, not reduction occurring. We have oxidation occurring, so we have to change the sign of this for oxidation because these are our standard reduction potentials. Okay, so we're going to find the potential for the copper-zinc galvanic cell shown right here. But I'm going to move this around a little bit. There we go. So this is what a typical cell looks like on the AP exam. They always set them up looking like this. We have one side and another side. Here's our salt bridge. We have sodium nitrate in the salt bridge. Here's our voltmeter. This thing is measuring 1.10 volts. If I open the switch, the voltmeter will read 0. The pieces of metal, the solid metal, those are our cathodes and anodes. So they tell you zinc is the anode. We look up the value for zinc. Let's see, where is zinc? Oops. Get out of here. We don't want you. Okay, so let's look up zinc. You just look over here, zinc, 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 zinc. I don't see it. I'm being a little bit slow right now. There it is, zinc. Right here, 0.763. Oh, there it is, negative 0.763. Okay, we're going to look up copper. Oh, and one quick thing. For this reaction, copper 2 is going all the way to copper 0, because they show you right here. Copper 2 going to copper 0. So we have to make sure we're looking up copper 2 going to copper 0. And copper 2 going to copper 0, positive 0.337. So these are our two standard reduction potentials for a zinc or a copper half reaction. Now, overall, this whole thing has to be positive, and one of these has to reverse sign. So you figure out which one has to reverse sign in order to make sure that when we add these together, we get a positive number. Well, if I have a positive and a negative, I'm obviously going to change the sign of the negative. And this will be my oxidation reaction. This will be my reduction reaction. Reduction, red cat, occurs at the cathode. The copper's the cathode. Funny, they made it red. Reduction. Okay, oxidation will occur at the anode, and we already said this one's going to get reversed, so we'll have oxidation there. So zinc will be the anode, and look, it is indeed the anode. Okay, and notice the voltmeter is showing 1.00. Those are our balanced half reactions. And the overall balanced reaction, the electrons are equal, so I didn't have to multiply the half reactions by anything in order to balance the overall reaction. And now, here's an interesting question. Where do the ions move and how do the electrons move? This is a thought process. So, the ions in here, they're already showing you where they're moving, but let's talk about why. So, on the copper side, copper 2 is becoming copper. Notice the copper 2 ions are disappearing. We need to replace that positive charge because the positive ions are reacting, going away, and they're becoming copper metal. So the sodium ions have to move over to this side in order to replace the positive charge that's lost as the copper 2 goes away. Over on this side, we are producing zinc 2+. See over here? Notice the products, we're making zinc 2+. So the zinc anode is producing some zinc ions, and now those zinc ions, they're making some positive charge over this side. We need some negative ions to make this side electrically neutral. So the nitrate moves over to this side. So the nitrate moves to the zinc side, the sodium moves to the copper side. Where are the electrons going? Well, notice zinc is making electrons, right? Zinc is going to zinc 2+ and making electrons. The copper is using up those electrons. So the electrons have to move from the zinc, over to the copper. They're going from the zinc anode over to the copper cathode, providing those electrons that join with those copper 2 ions to make copper metal. And what you physically see happening, you should write this down in your notes. The copper cathode gains mass. The mass gets bigger because we're producing copper. The zinc anode, the mass actually gets smaller because we are using up the zinc atoms to produce zinc ions. And this thing gets smaller. This cathode gets larger. Okay, new problem. So we want to find the cell potential and the balanced reaction for this. Okay, so we just look up the half cells. You can look them up over here. You look up the aluminum and the magnesium. They're on there. Just look them up. And aluminum, magnesium. Now we have to figure out the cathode and the anode. Magnesium got oxidized. Oxidation is the anode. Aluminum got reduced. Reduction is the cathode. And remember the equation? E cell is the cathode minus the anode. Remember, these are reduction potentials. If you are oxidizing something, you change the sign. Whatever is getting oxidized, you change the sign. So you could say E cathode minus E anode. And we just plug it in, and here we go, 0.71 volts. Balanced reaction. If you want to balance this on your own, go ahead. We have 3 electrons and 2 electrons. We're going to have to balance our electrons. Okay, you should have paused if you wanted to do it on your own. If not, there it is, done for you. We had to multiply the top reaction by 2, the bottom by 3, till we could cancel out the electrons, and this is our overall balanced reaction. Big note here. We are multiplying these by numbers, but notice we don't multiply E cell by those numbers, which is really strange. When we did Hess's law, if we multiply reaction by a coefficient, we multiply delta H by that coefficient. We do not do that with E cell, and that is written down for you. And this explains why. It's because of the units of volts. They're joules per coulomb. Joules is how much energy. Well, if we multiply, we should get double the energy. We multiplied this by 2. We should double the energy. Coulomb is your charge. Well, we also doubled the moles of electrons, so we doubled the charge. We doubled the energy. We doubled the charge. So when we do energy divided by charge, energy divided by charge, that number stays the same. It's when you reverse the reaction, you do change the sign for the voltage. Okay. Oh, big problem here. Lots of questions. Okay, see if you can figure this out on your own. You can pause this if you want to look everything up, but I'm going to just go through it right now. So we have to first figure out which of these is going to get reversed. Oh my goodness. Okay, so we look up the E cells on that table on the previous page. It's right there. So we look up the E cells. Oops, oh goodness, that's not what I wanted. And we figure out which one do we need to reverse. Let's see, this is less positive. I'm going to reverse this one, because if I reversed the silver one, I would get a negative E cell when I added those together, and E cell has to be positive. So I will reverse this one. Okay. And then E cell is E cathode minus E anode. There's E cell. Standard cell potential. Okay, now to balance the reaction, I have 2 moles of electrons here, 1 mole here. I have to double this overall reaction. Here's my balanced reaction. Cathode and anode. Cathode is reduction. Silver gets reduced, so silver is the cathode. Cathode and anodes are solid. The anode, oxidation. Copper got oxidized. Copper's the anode. Remember, an ox and a red cat. Okay, now which way are those ions moving? Let's just look at this overall balanced reaction. Silver ions are getting used up, so the positive ions from the salt bridge have to go to the silver side. Copper 2 is being produced. I have to neutralize the positive side, so the negative ion from the salt bridge will go over to the copper side to balance out the positive charge produced on the copper side. Now let's see, who's using up electrons and who's producing electrons? Copper is going to copper 2. Copper is making up electrons. Silver ions are becoming silver. They're getting used over at the silver side. So the electrons are going from the copper side to the silver side. The electrons are going from the copper over to the silver. And here is everything I think I just talked about. Okay. On to section 17.3. Cell potential, E, not cell. Electrical work and free energy. If you ever see EMF, that's the electromotive force. That is your cell potential. It's your work or energy over the charge, coulombs. We have an equation. Delta G is negative NFE. Where? N is your moles of electrons transferred in the balanced reaction. You have to be very careful. You have to have your balanced reaction and see how many moles are transferred. F is Faraday's constant, 96,500 coulombs per mole of electrons. It's the charge of a mole of electrons. Okay, so first problem. What is the Gibbs free energy for problem 1 in section 17.2? We're just going to, you can pause this, plug in the information, see if you can do it yourself. You use the E naught, the moles of electrons transferred, and Faraday's. Just look it back up in problem 1. We have the voltage, and we see there's 6 electrons transferred. You just plug it in, voltage, 6 moles of electrons. There you go. If I calculated that wrong, you should let me know. I did convert this to kilojoules. Okay, same thing. Go ahead and pause. Try to do this on your own and look at problem 2 for the voltage, moles of electrons. There we go. I'm hoping I got that calculated correctly. Notice it's kilojoules. Okay. Section 17.4, last section, dependence of cell potential on concentration. So we've been talking about these standard cell potentials. That's 25 degrees Celsius and 1 molar. It's assuming concentrations are 1 molar, pressures are 1 atmosphere. Actually, there's no such thing as a pressure in these galvanic cells because they're in liquids. Okay, so the chart that we've been using, standard cell potentials, 1 molar, 25 degrees Celsius, 1 atmosphere. And we can use Le Chatelier's principle. If the products are higher than 1 molar, the reaction is driven to the left. If the reactants are higher than 1 molar, the reaction is driven to the right, making the thing more spontaneous, higher E naught. If the products are greater than 1 molar, then the reaction would be driven to the left by Le Chatelier. And that makes the reactions less spontaneous if the reaction is driven left. So E naught would go down. Okay, so here's a problem. You think about this, and you're about to see the reaction, so pause or look at the reaction. Sorry, you had to actually see the problems in order to pause. There's your 2 problems, and I'm about to show you the solutions. This is the reaction. So you're looking, is the product going up or is the reactant going up? All right, for A, magnesium, product larger than 1. The reaction is driven left. Therefore, the reaction is less spontaneous. No, I read that wrong. Sorry. Aluminum is 2. Aluminum is bigger than 1. The reaction is driven to the right. So sorry about that. And the reaction is more spontaneous, larger E cell. And notice we lost the naught there because that's no longer a standard cell potential since the concentrations are not 1 molar. We lose the little naught, that little naught right there. We lose that when we have non-standard concentrations. For B, magnesium is bigger than 1. And I have a misspelling there. Fixed that. I can spell concentration. So for B, magnesium is 2 molar. Products are bigger than 1. So the reaction is driven less to make it less spontaneous. So the cell potential should go down. And that's it on this section. There's a little bit more. Okay, we are now looking at the Nernst equation. So we're still looking at concentration and standard and cell potentials, not the standard cell potentials. And the Nernst equation gives us a mathematical equation that relates E naught cell concentration and the non-standard cell E cell. And here's our equation. This is as you will see it on the AP exam. R is the gas constant, and we always use the R 8.314 joules per mole Kelvin because this is an energy unit, energy, and R is in joules. We need an energy unit, so we use the joules, not the atmospheres. N is moles of electrons. F is Faraday's constant. Q is the Q from equilibrium. It's the reaction quotient, which your initial conditions are. And that is equal to this at 25 degrees Celsius. Under standard temperature, we just plugged in temperature and R, and Faraday's constant, that 96,500 coulombs per mole electrons, and this is what we get out of that. Okay, so here is a problem. Find E cell for an aluminum, aluminum 3, manganese, manganese 2, galvanic cell at 25 degrees Celsius, so we get to use this equation, when the aluminum ion is 1.5 molar and the manganese 2 ion is 0.5 molar. So we have to find E cell. Here's just the method. You can pause this and try it completely on your own if you'd like. I'm going to move this down a little bit. We get E cell just by checking the manganese and the aluminum, seeing which one we have to reverse in order to have a positive E cell, standard cell potential. Standard cell potential. Then we have to balance that equation to get N, our moles of electrons for N right here, and then plug in these into the Q and plug it all into the Nernst equation and solve. So here we go. So we look these up. Oh, manganese 2. It's in your book. I'm so sorry. I don't think it's on the sheet that I gave you on the first page. That particular website that I used to get that did not give manganese, so I had to look it up. The AP exam has that value for you, and you will get that in class. Okay, here's your half reactions. We got to figure out which one reverses. I look at this and I see immediately this one must reverse in order to get a positive overall E0, because this one is more negative than this one. You have to get really comfortable with positives and negatives in this particular chapter. Okay, and E cell, E cathode minus E anode, cathode, reduction, this is reduction, so we leave that the same. Anode, oxidation, this is getting reversed, so we will have oxidation. We subtract this E naught, we get 0.48 volts. That's the standard cell potential. Now we gotta we have to balance it first. We gotta balance the electrons, multiply the top by 3, the bottom by 2. There's our balanced reaction. Hope you recognize that means there's 6 moles of electrons. For this reaction going through one time, there would be 6 total moles of electrons being transferred. Plug that into the Nernst equation to get this. We are almost at the end. Okay, we're done with that problem. Now, we really are at the end, and this is one of our most exciting moments in chemistry. You're about to learn something very important. Okay, this is Q right here. If Q is K, we are at equilibrium, right? If we're at equilibrium, the cell potential is 0. There is no cell potential. At equilibrium, nothing's going on. So we plug this as 0, because E cell will be 0 when Q is K, so we plug K in for Q, 0 for E cell. We move things around. We get this equation for K. And now, fantastic, we have equations that allow us to calculate K, delta G, and standard cell potential from any of these 3 values. We've learned earlier how to get delta G as negative RT ln of K. And we have K to E. So if we have any of these 3, we can get the other 2. And that is the end of this lecture.